In this tutorial, we're going to look at spectra that are coming from stars. In particular, we want to try to develop our intuition a bit for how the shape of a spectral curve can tell us something about the temperature of a star. So we have absorption line spectra for 6 hypothetical stars. I'll just pause for a second. So anytime we look at a star, we're going to see an absorption line spectra because we're always going to have cooler, lower density material on top of hotter, opaque material. All right, absorption line spectra for 6 hypothetical stars, each with different temperatures, are shown below. For each absorption line spectrum, the short wavelength of light, or blue end, of the electromagnetic spectrum is on the left, and the long wavelengths of light, red end of the spectrum, is shown on the right side. And so we have a star at 30,000 Kelvin, 24,000 Kelvin, 20,000, 18,000, 12,000, 8,000. Do cold stars always appear to have a different, greater or fewer, number of lines in their absorption spectra than hot stars? Cite evidence from the above spectra to support your answer. Just go through and count them up quick. This one has 5. That's also 5. This one has 6 absorption lines. 6 absorption lines. 5, 4. Do cold stars always appear to have a different number of lines in their absorption spectra than hot stars? So the hottest star has 5. The second coldest star also has 5. And the coldest star has 6. So answer is no. Do cold stars always appear to have more lines at either the blue or red ends of their absorption spectra than hot stars? Cite evidence from the above spectra to support your answer. Well, like this star, the coldest one has 2 at the blue end, and so does star A, which is the hottest. It has a triplet of lines to the red end. The next hottest star also has a set of lines at the red end. So splitting it up blue and red end doesn't give us a pattern either between temperature and absorption line locations. Consider the absorption line spectra given below for star G. Can you determine the approximate temperature for star G by comparing its absorption line spectra to the absorption line spectra and temperatures of stars A through F given above? If so, write in your estimate in the space below. If not, explain why not. So star G has got a single line to the blue end. It's got a pair of lines in the middle and a single line to the right. It's 4 lines overall. Those 4 lines don't look anything like the 4 lines in star B. Star F has 1 line over to the left on the blue end like this, but it doesn't have a pair in the middle, and it doesn't have just 1 to the right. So this spectrum, that pattern of lines, isn't a match to any of these stars. So it's not looking at it in this gross level of just where do the lines fall that is going to tell you what the temperature is. You can work that out, but that is a more complicated affair than what we're going to do in astronomy at this level. So, while it is difficult to directly estimate the temperature of a star from the lines in the absorption spectrum, we can always use the wavelength of the peak for the light emitted by a star to estimate temperature. So that's Wien's law again. The spectral curve on the graph at right illustrates the energy output versus wavelength for star G. The same star G is on the previous page. Again, the short or blue wavelengths of light are represented on the left side of the horizontal axis, and the long or red wavelengths of light are represented on the right end of the horizontal axis. So let's sort of try to go through what we're looking at. So this is basically a top-down view of the spectral energy curve. So there's an absorption line, which is this one. There's a pair of absorption lines, so that pair. And there's the fourth absorption line is this one. So star G's spectrum is peaking right about there, sort of in between those two absorption lines, so the peak is actually right around there. There are two important features represented on the spectral curve that you need to consider. The exact locations of the small dips or absorption features on the curve occur at the same wavelength as the dark lines that appear in the absorption line spectrum shown on the previous page. The wavelength at which the object's peak energy output occurs is directly related to the object's temperature through Wien's law. Hot objects have their peak energy output at short wavelengths towards the blue end of the spectrum, and cooler objects have their peak energy output at long wavelengths toward the red end of the spectrum. Although the total energy output of a star is affected by its temperature, and therefore so is the height of this spectral curve, for this activity we'll assume that the height, but not location, of the peak energy output and the general shape of the spectral curve for stars A through F can be drawn nearly the same for each star. That's not actually true, but that's not what we want to worry about in this tutorial. So only the location of the peak intensity and the location of the small dips or absorption features will be different for each star. So let's examine the spectral curve shown at right for star A, same star A as on the previous page. Note that star G has a temperature of approximately 25,000 Kelvin, whereas star A has a temperature of 30,000 Kelvin. With this information, would you say that the location for the peak of star A is drawn at approximately the correct wavelength as compared where the peak of star G is drawn? So star A is a little bit further to the left than where the peak was for star G. So it's at 1, 2, 3 and a bit. And this is at 1, 2, not quite 3. So that might be a 5,000 Kelvin difference. It's hard to say because there's not actually any units on this, but it is at least in the right direction. So approximately right. C. Are the absorption features dips in the spectral curve for star A at approximately the correct wavelengths? Explain how you can tell. So let's go back to spectrum A. I've got a pair of absorption lines on the left, and then I've got 1, 2, 3 absorption lines to the right on the red end of the spectrum. So that looks roughly right. Okay, I'm going to try some more art, and it is probably going to continue to go badly, but I shall persevere. We are to sketch spectral curves for stars B through F on the corresponding graphs provided below. Do not worry about whether the height of the spectral curves you draw are accurate, but make sure your spectral curves indicate the absorption features and the peak intensities drawn at approximately the correct wavelengths. So star A is the hottest one in our sample, and that's the one where the peak should be furthest to the left. The next hottest star in our sample is actually star F, which is at 24,000 Kelvin. So its peak should just be a little bit to the right. So I'm going to try to draw that one in. So this one is at 1, 2, 3. So this should peak about there. And I need to have an absorption line on the way up to the peak. And then I've got another absorption line. And then I need to have 1, 2, 3, 4 absorption lines as it goes down over towards the red end. Oops, absorption, not emission. So something like that. All right, the next hottest star is star B, and that one, I need to have the peak just a little bit further to the right still, at 20,000 Kelvin. And I'm going to have 3 absorption lines as I go up to the peak, and then 1 absorption line far to the right. So something like that for star B. Next hottest is star D. So draw that in. So I'm going to need to move the peak a little bit further to the right. And now I've got sort of 2 on the way up, 1 near the peak, and then 2 at the red end. And then star D, I have 2 as I go down. So something like that. Next coolest star is star C, and then the coolest star is star E. So star C, I need to move the peak a little bit further to the right still. So we're following Wien's law. I've got 3 on the way up, 2 on the way down. Something like that. Should be more of an absorption line than an emission line stuck on. So that's not a great drawing. All right, and then star E, this would be the one where the peak is furthest over to the right. I'm going to have 2 absorption lines as I go up. I'm going to have 1 near the peak and then 3 on the way down. And try to make the peak as far over to the right out of this set of 6. So 2 on the way up. And then 1. And then 3 on the way down. Something like that. All right. Did you draw the peak intensity of each spectral curve at the same wavelength as the spectral curve for star A? No. At least I tried not to do that, and I can't. Because of Wien's law, peak wavelength changes as the temperature changes. If you were given a star's absorption line spectrum and its corresponding spectral curve shown on an energy output per second versus wavelength graph, how could you approximate the temperature of the star? So not from the pattern of absorption lines per se, but from the location of the peak in the spectral curve. So we could use Wien's law to find the temperature. All right, and then this time we have a student making a statement. Consider the following statement made by a student regarding a star's temperature and its corresponding absorption line spectrum. If I am looking at a star's absorption line spectrum and see that it has a lot of lines at the blue end of the spectrum, then the star must be hot because the blue lines are higher energy lines. And that, not true. If I want to say something about whether the star is hot or cold, I actually have to look at its spectral energy curve to see where that curve is tallest of allest. And the shorter that wavelength where it peaks, the hotter the star is. Bluer stars are hotter than redder stars.